Okay, we start up again. That's an example of a compressible flow here. Flow around a cylinder. It's a two-dimensional flow, but the Mach number here is pretty high. It will be around 3 or something like that. So yes, we're going to get some shock waves around this cylinder. And to be able to capture it, you actually need a quite decent mesh around the surface here to catching this mesh, the shock waves. So here I have some animations of this one, and it's quite nice. And as you can see from the time, it develops rather rapidly. And then you get a steady state situation here. So yeah, now nothing changes. So going back to where were we? Now I missed it. Here we go. And here we go. So that was Mach numbers for this animation. You have another option, they call it Schlieren contours. It's possible to create them, but then you have to do a little bit calculations first. You need the divergence of the density gradient to show the change in the density. That's sort of what they call Schlieren contours. And well, it's actually just the same roughly image. You get the same structure here. So we might as well just show the Mach number, local Mach numbers. We don't have the Mach numbers as a variable in our simulation, so that one has to be calculated afterwards. But that's okay. So for this setup here, they have set up some hints how this one can be actually done. And I must admit, I tried to do this, tried to simulate that one, and I couldn't make it work. It crashed all the time. So it's not necessarily so easy to set up such a problem, or it's just me that are stupid. It crashed because I got negative temperatures, and that's not so good. The temperature should be absolute here in Kelvin, so when that one goes negative, then not good. So yeah, it should be possible to limit him to say, I want a temperature in this range, just to stabilize the simulation. Also the pressure can be stabilized, that he shouldn't go lower than 10% or maximum than 1000% of what you have. Also you can limit your velocity, setting a max velocity. I don't think you can set a minimum velocity. It should be 0 anyway. So these simulations, can be rather edgy. It's also possible to use direct numbers here for the pressure. Instead of using these values here, you can set actual numbers if you want. That's also an option. So these limiters here, they might actually be important. Okay, so far this shock waves. See if I can make it work later. I did find one tutorial which was actually quite nice. It was called forward step. I can just show you the forward step. I think I run it, yes. So here you have the following setup. So you have an inlet here, and then you have a forward step, and then an outlet, and then wall, wall, and it's a two-dimensional thing, and you don't have many cells here. And here they have done it a little bit strange. If you look at the velocity that we send in here, the velocity is 3 meters per second. But they have played around with the numbers. So in this world, the speed of sound is 1 meter per second. Meaning if you send in a velocity of 3, then you actually have a Mach number of 3 already here. So it's a little weird. But let's see how it looks. When you simulate it, you get something strange maybe. If you look at the temperature, yeah, also develops a little bit strange. Pressure, also a little bit strange. And then finally they have here evaluated the Mach numbers. So here you can see the initial state. You have sent in a Mach number of 3, and then something happens with the Mach number here. And this is something we have to look at as a steady state, or at least towards a steady state setup. You see the Mach number, it goes down. And let's see, we have one roughly this color. So here we'll have a Mach number of 1. And that's something physical actually, when you have a nozzle and when you have the area, which then is the smallest area, you will always find Mach number 1 there, regardless of whatever driving force you have in the system. We're going to see more of that one later. To see the shock structure here, I think it's better than to have a look at time level 2 or something like that. Where are we? You get some very nice shock waves, and of course, yeah, you get some reflections from the walls. So it's a nice, nice and cute little problem. So you should be able to find it yourself and play around with it. Any questions to that one? The name of it was then, what was it? Forward step, at least on my distribution. Okay, then we have to jump to a little theory. I wanted to simulate this nice supersonic cylinder flow here. Because what's interesting, we have a free flow and then heating an object. So yes, you'll have a stagnation pressure here at the surface. And that example is what I'm going to look a little bit into now. I don't have any decent chalk. So this then will be a little bit about, say, gas dynamics theory you maybe have seen before, but never mind. First of all, speed of sound. How do you find that one? Speed of sound. Well, you can actually find the acoustic wave equation fairly easy. And I'm not sure if you've seen this one before, but then you'll find the speed of sound A should then be equal to, and it will be something like this, the square root, and then the change of the pressure versus the change of density. And here it will be at a constant entropy. So a lot of people use S. OpenFOAM uses H, never mind. So yeah, we have something like that. And then if you look at an adiabatic system, adiabatic, and actually also it's reversible, so you have no loss of thermal energy or something like that. Adiabatic, then you should have the pressure divided by the density to the power of, some people uses kappa, some uses gamma. It's actually a constant thing. And then we can use an ideal gas law. Pressure equals rho R and then the temperature. Then it's possible then to find, this one then has to be the square root of, what will it be, gamma RT. Which then should be 330 meters per second in air or something like that. So yeah, we can find the speed of sound, an expression for it. Should be possible. So, yeah, we do it easy here. I want to look at a stagnation flow. And I mean, this one should be familiar to most of you. So you send in, say, a free stream here. We'll have a velocity, u infinity. We will have a density. Well, we could use the pressure here. Well, we need the density as well. So you're sort of looking at this, say, relatively. You will have an object actually moving through air, gas, that is standing still. So we just look at it relatively. And then, of course, the streamlines will go around this one, but we'll have one streamline hitting the exact stagnation points, S. So you compare these 2 points, and when you're now using the Bernoulli equation, you do it simple. We neglect gravity, we neglect friction forces, we don't, they're not important here. But we have to use a compressible version of the Bernoulli. So what will it be? If you look at this streamline going from here to here, then the situation over here, you will then have the velocity squared half, and then comes the pressure terms. Normally we will write that one for an incompressible flow, that's just pressure over density. But here we need the gamma over gamma minus 1, pressure over density. Whether you use kappa or gamma, your choice. It's just a constant, the ratio between the heat capacities. For air, what was it, 1.3 or something like that, I think. No potential energy, so we skip that one. And then this one equals, and then you have the situation in the stagnation point. Well, then we don't have a velocity. We just have the pressure, but I still need the same sort of adjustment, adiabatic process, gamma over gamma minus 1, and then I'll have P stagnation minus density stagnation, like that. One question when you do it like this, you look at it relatively. As I said, it's actually air standing still, and this object moves with a velocity u infinity. That's actually what's happening. But then, haven't I done it wrong here? Because here I said I have a velocity at infinity, looking at it relatively. What if you look at it absolutely? You're just standing on the ground and looking at the situation. You have an object flying with a speed u infinity. Well, then the situation over here doesn't have a velocity. But this one have a velocity, so then plus u infinity should be on this side. And then also you see something strange. Here you now have the stagnation pressure. It will equal the surrounding pressure plus the dynamic pressure. Makes sense. Stagnation pressure will increase. But what if I look at it absolutely? It will be quite different. Then I have the stagnation pressure equals the surrounding pressure minus the dynamic pressure. That's totally crazy. Why? I mean, we have to look at it relatively. Why? The Bernoulli equation is, I guess, the equation that is most violated of all the equations. Because you have a long, long list that has to be fulfilled before you're allowed to use Bernoulli. One of them will be either your flow is has no vorticity, the curl should be 0. We can't really say that here. Or you have to move along a streamline. Your 2 points has to be on the same streamline. Okay? When you look at it relatively, then you have a nice streamline pattern around this object. If you look at it from an absolute view, you don't have any streamlines at all. You can't go from here to here along a streamline. It's not valid. That's the reason. So, yes, we get this one. And yeah, we can now rewrite that one. Shouldn't take too long, this one. Yeah, I have to remove this. So yeah, we can rewrite this one quite easily here, just using ideal gas law. Pressure divided by the density. Ideal gas law says this one is equal to the gas constant R multiplied with the temperature given at infinity, while this one will then be R and then the temperature in the stagnation point. So you can rewrite this equation quite easily just looking at the temperature. So now we are talking how hot will it be in the stagnation point. And that one will now equal, and then you will have something, something, something. Let's see now. We have to multiply with gamma minus 1 over gamma, and then move this R on the other side. So it will be something like this, I guess. Plus 1/2 u squared, and then we have to multiply gamma minus 1 over gamma, and then finally 1 over R. And then with a little algebra, put T infinity on the outside. Then you will have 1, and then we will have something like plus, let's see now, gamma minus 1/2, and then you'll have u infinity square divided by, and here you will then have gamma R, and then you will have T infinity. What's this ratio here? There you find the Mach number squared. Because square root of gamma RT, that's the speed of sound. And then, yes, this one will then be the Mach number. So you will have it as 1 plus gamma minus 1/2 Mach number squared. Actually, it's Mach number infinity, but never mind. Yeah, we call it M infinity then. Something like that. So there you can calculate your stagnation temperature depending on the Mach number. And as I said, when the space shuttle comes in from outer space and hit the atmosphere, we have a Mach number of 25. Thank you very much. 25 squared. Hence, the temperature is going to be increased to 20,000 degrees Kelvin or something. So your space shuttle is going to melt. Very sad. So what do you do? Well, first of all, the theory doesn't apply. When you have a Mach number of 25, then it's not a continuum anymore. So you have to use kinetic gas theory and stuff like that. And also, when you hit the first air molecules, nitrogen is going to doesn't dissociate and sort of steal the energy away there. So no, they don't melt, but they need some heat shields. Okay, that was the temperature, and now we replace this one with pressure. So if we now say we have an adiabatic system here, let's see, we had, what did I call it, stagnation, scaled with the infinite pressure. And then for the ideal gas law here, we will have rho stagnation, RT stagnation, by rho infinity, RT infinity. And then the adiabatic says this should be the same as rho stagnation minus rho infinity to the power of gamma, something like that. And then you can replace this ratio here. If you divide by T infinity here, you can then find the following. I need more space. So I want the rho S over rho infinity would now be equal. That should then be Ts over T infinity to the power of 1 over gamma minus 1, something like that. And that one will apply. I don't want density, I want the pressure. So the pressure in stagnation point, scale on the surrounding pressure, will now then be equal. And then you will have temperature ratio, and then it will be to the power of gamma over gamma minus 1. There you have it. And then you can insert the answer here. So you will have 1 plus gamma minus 1/2 Mach number squared to the power of gamma over gamma minus 1. Okay. Stagnation pressure equals something like this. Now, this is a rather messy expression, but you could use a simple series expansion here. So 1 plus x, I think I used x, didn't I? Yeah, to the power of n. That one can be expressed as 1 plus x times n, and then you will have plus, what will it be here? N times n minus 1 over 2 faculty times x squared plus yada yada yada. This is a standard trick. All the physicists are using this one. So you sort of change a nasty expression to a series, and then you use only the 2 first terms. Sometimes even only the first one. Very crude, but this is okay for small x's. If x is not too big, meaning this one shouldn't be too big. Keep that one in mind. Okay? Then how can we rewrite our pressure expression here? Let's see. He will then end up with something like this. You will have the pressure in the stagnation point equals the surrounding pressure, and then you multiply, no, not there. We will have plus, and then we will have 1/2 velocity squared, and then the density squared. So there you have surrounding pressure plus the dynamic pressure. But here now you will have 1. That is if you only take the first one. This is from incompressible flow. I mean, the stagnation pressure equals surrounding pressure plus the dynamic pressure, and nothing more. But here you will now have 1/4, and then you will have the Mach number squared, and then higher order if you had taken the second, third, and so on. So there you see the adjustment due to the Mach number. If the Mach number is not too big. Small x, meaning smaller than 1 at least. So here is then the point. If I have a Mach number of 0.3, what will I get here for this term? Well, you have 0.3 times 0.3, it's 0.09. Then you take a quarter of that one. So you have an anode, which then will be 2% or something, wasn't it? Yeah. Anode 2%. That is where we have this limit, Mach number 0.3. When you don't have a velocity in your flow more than 30% of the speed of sound, then you can neglect the compressible effects altogether, because the effect is definitely very, very small indeed. But bigger than 0.3, then this one quite rapidly starts to grow, and then the entire theory here breaks down. Then the x is not small anymore. So then we have to do something a little bit more tricky. But I just wanted to show you where this 0.3 came from. Yeah?
In the middle equation, I don't understand how you pass from the second to the third term.
I mean this one?
Yeah, in this equation. It's not the ps over p infinite.
So, I mean, here I just inserted what I had.
Yeah, but just before.
Oh, you mean this one?
Yeah, this one. Why is it like to the power 1?
Here it should be, I removed the 1 here. Like, this is what you have then, and then you change from density to pressure. That's the adiabatic relation, saying that pressure by density to the power of gamma is a constant thing. I just use that one.
Okay.
So that's why I get another gamma at the top.
But then why doesn't it have power 1 over gamma on the ratio of p?
Sorry, where?
On the ratio of the p ratio.
I mean this one?
Yeah.
Yeah. Satisfied?
Okay.
Other questions? Yeah.
From where do we get the 1/4?
Let's see now, 1/4. When you insert here, let's see, you multiply this one down here, gamma minus 1 disappears. You are then left with, what will it be here? Gamma half. So you'll have 1/2, and then let's say gamma 1/2 should be, how did I get 1/4 after that one? No, it should be there, I think. Gamma minus 1/2, gamma, well, roughly 1/2, roughly 1/4. I mean, of course, it will depend on the value of the gamma half, but gamma half should be roughly 1/4, I believe. Yeah, at least a number definitely smaller than 1.
I mean, the gamma shouldn't be always like.
Sorry?
Gamma should always be greater than 1.
Yeah, but not gamma half.
Yeah, but then it should be always be greater than 1.
Yeah, okay, so if you put 1 over 6 here or 1 over 7, I don't care. It's still a small one. But I think it's correct. I think it should be 1/4. I skipped some calculation here, but I think it should be correct. Gamma. Minor detail. Other questions? So next week then I will continue a little bit more with gas equations, looking into convergent divergent nozzle, Laval nozzle, and see how this shock waves shows up. How far can we go with analytical theory? And when do we have to start simulating, because we can't do it by hand anymore. But that should be the topic for next week. Any questions? And we stop here.